At this point, we have this map rep BD that when you fix a vector space V with basis B, a vector space W with basis D, we get this map from the collection of all linear maps from V to W to the collection of matrices of size Mn. We've seen that each of these individually is a vector space, and so the natural question to ask is rep BD, and is it a linear map? We know already it's well defined, and we explicitly constructed an inverse map, so we know that there is an inverse, right? That inverse is the map that takes a matrix to this crazy thing here, right? Remember, so this is the matrix. This is the linear map that you start up you start up here with a vector. First, you take its representation relative to the basis. Then you hit it with the matrix A by doing this matrix vector multiplication. And then you do the inverse of representation with respect to D, and that gives you a vector over in W. And that constructs we checked that is a linear map from V to W. So we have an inverse for this function rep BD. The only question is it actually a linear map? If it is a linear map, well, since we have an inverse, we know that it has to be one-to-one and onto, and so it will be an isomorphism. So let's check if it's a linear map. What would that actually mean? Well, right, how do you check anything as a linear map? You take two things in the domain. So for us, these things in the domain are themselves linear maps. So excuse my bad L, my bad script L. So G and H, these are linear maps from V to W, and take two scalars, maybe we'll call them A and B, in the real numbers. And what we want to show, so WTS is want to show, we want to show that rep BD preserves structure, so we need to show that rep BD applied to the linear combination AG plus BH is equal to the linear combination after doing the representation. So that's A times rep BD applied to G plus B times rep BD applied to H. Right. Right. This is just, if you look at this equation and squint so that the name of the function gets blurry, this just says we're preserving structure. The fact that the name of our function is complicated, representation relative to BD, doesn't change the fact that we're still just checking that this map preserves, this function preserves structure. So we will know it's a linear map. So we don't know this yet, right? This is what we're trying to show. Keep in mind that everything here is a matrix, right? So this is in Mn. This matrix is in Mn. This matrix, rep BD of H, that's in Mn. And so on the right-hand side of this equation, these scalar products and this addition, these are all happening in Mn. And these scalar products on the left-hand side and this vector addition, these are happening in the space of linear maps from V to W. Right? Okay, so right, we're checking that this representation map translates the vector operations in the domain vector space into the vector operations in the codomain vector space. Okay, so how can we check that these things are equal? Well, these things are all matrices, right? This is a matrix, this is a matrix, this is a matrix. How can we check that matrices are equal? Well, we could write down everything in terms of the entries of all of these matrices. That sounds like a real mess. It's not impossible, but it just takes a ton of writing. You just write G with a bunch of subscripts, and it's a pain, frankly. But it's not hard either. But to get sort of another view on why this should be true, remember we have another way we can tell that two matrices are equal. Two matrices are equal if if multiplying them by any vector gives you the same result. So what we can do is multiply rep BD AG plus BH. We can multiply this by any vector, right? And what we'll do is we will compare this to what happens to the matrix on the right when we multiply by the same vector. So if we can show that these two are equal no matter what the vector v is, then we're done. So as we do this, keep in mind that this vector v is, based on notation, you'd assume it's in the vector space capital V, but it's actually in Rn, right? So we're living down here. It has to live in Rn or else this matrix vector product isn't defined. So we are trying to figure out what happens when we use this matrix, rep BD of AG plus BH. What happens when we go over to Rm? Well, we have rep BD is defined so that using this matrix, rep BD AG plus BH, to get over along the bottom side of this square is the same thing as going along these three sides, right? And then going horizontally, we do AG plus BH. So let's do that. How do we get up here? What map takes us from Rn to V? Well, remember, the left-hand side here is the representation map for V. So to get from Rn to V, we do rep B inverse, right? So this is the same thing as, so start with V, do rep B inverse to get to V. Then you do the linear map, which is AG plus BH. This is supposed to be an A. Okay, that's across the top. Then you go down the right-hand side, and this is rep D. Okay. Now there's a lot going on here, so this is a big composition. We're starting with V, and then we're doing three things to it. First, inverse of rep B, and then this linear map, and then rep D. But now that we have things written this way, this right here, what is this linear map? What does this linear map do to this vector in capital V? Well, just by definition, how do you add and do scalar multiplication in a space of linear maps? You do it pointwise. So this is A times G of rep inverse B of V plus B times H of rep B inverse of V. Okay. Now, rep D is also a linear transformation, relative to any basis. The representation map going from a space to a Euclidean space is a linear transformation, and so we can use the fact that rep D preserves structure. So then we get A times rep D of G of rep B inverse of V plus B times rep D of H of rep D B inverse of V. Okay, so this is A of, so what is rep D of G of rep B inverse of V? So if you start with V and you do, you go up using the inverse of rep B, and then you go over using G, and then you go down, what do you get? Well, that is the definition of, well, it's not the definition, but we know that it's equal to rep BD of G times the vector V, right? We essentially defined matrix vector multiplication to make this the case, okay? But then the same thing happens over here. B rep D of H of rep B inverse of V, that's rep BD of H times the vector V. But look, that's what we wanted, right? We wanted to show that, and this is for all V. So for all V in Rn. So what we've shown is that for every vector V, these two things are equal, right? Because we started with this one and we produced that one. Okay? So for every vector in Rn, this product is equal to that product. But we know that that means that these matrices have to be equal. So this matrix is equal to that matrix. But that's exactly what we needed to know that rep BD is a homomorphism, is a linear map, a homomorphism. So we know it's a linear map. So now we know that this thing is an isomorphism.